Unit 5 Thermochemistry, pages 17 to 21, State and Path Functions. State functions. Certain quantities like mass, height, and color depend only on the state of the system and not on how the system was prepared. These quantities are called state functions. Other quantities like heat, work, and time depend on how a process is carried out. These quantities are called path functions. So, state function depends on the state of the system. Path functions depend on how the process is done. So here's an example of a state function. Consider two states in the growth cycle of a flower, state 1, state 2. And they end up at different heights. Quantities like height, mass, color define the state of the system. These are state functions. State 1 is defined as a flower with 10 centimeters height. The fact that the height is 10 centimeters does not depend on whether the plant was bought at Walmart or raised from a seed in your house. The change in height for this growth process is delta H. The difference between heights of a 60 centimeter plant and a 10 centimeter plant is a state function that depends only on the two states, 60 centimeters and 10 centimeters. So delta H is your final minus initial height, which we get here. Path function example. The time to carry out the change in state for the flower is a path function. Time depends on how the process is carried out. For example, the quantities of light and water determine how fast the plant will grow. Heat and work are path functions. Consider a fully charged battery containing 75 joules of energy that is discharged to an energy of E final 0 joules in two different ways as shown below. Since 75 joules of energy is drained from the battery for both paths, the change in state is the same for both. In other words, they both end up with the same final energy, and so that would be a state function. However, the path to get there is different for each of them. Here's path 1 through a resistor with heat, energy to heat. Path 2 is going to be energy to work. Energy is a state function, and delta E is the same for both paths. However, heat and work depend on how the battery is used. In path 1, all the energy from the battery is converted into heat, and in path 2, all the energy is converted into the work of the moving fan. So here's path 1, where the energy is negative 75 joules, and you have heat that's negative 75, but no work was done. And then in path 2, the energy is the same, so that's the state function because they both end up the same at the end. But this is the path function where the heat is 0 in this case, but the work is negative 75 joules in this case. Heat and work are path functions. The value of heat and work depend on how the process is carried out. Summary of state functions. This is a comprehensive list of functions that we will see in this course. Delta H, delta G, delta S of the system will be introduced at a later time. So these are all going to be considered state functions, and notice these are our path functions: heat, work, and time. Mass is a state function in isolated and closed systems where mass is not exchanged with the surroundings. This brings us to our first law of thermodynamics. Thermodynamics group energy into only two forms called heat and work. The first law of thermodynamics says in all chemical and physical processes, energy is conserved. So the delta E is going to be equal to the heat plus the work, where delta E is a state function. Q and W, heat and work, are both path functions. Notice that we never use delta for the path functions Q and W. The first law of thermodynamics says energy is conserved. Recall the experiment where the battery was discharged along two different paths. Notice that heat, Q, and work, W, have different values for the two paths. This is expected because heat and work depend on path. However, delta E is the sum of the heat and the work together, and it's going to be the same for both paths as predicted by the first law of thermodynamics. Here's your note card for this section. State functions are going to be the same regardless of the path, and this is your list of things that are state functions. Path functions are going to depend on the path that's taken. So here are your path functions. Time, heat is Q, and work, W. The first law of thermodynamics says that energy is conserved. So delta E is going to be equal to Q, the heat, plus W, the work. What you're going to have to focus on is, remember from our previous video, whether or not the heat and work are going into the system, so whether or not they have positive values, or are they exiting the system, which is going to give them negative values. And so those are going to come into play when you're calculating your delta E. Watch out for these. If you see at constant volume, well, then there's no expansion or contraction. No work is being done. So work is going to be equal to 0. If something is at constant pressure, then the Q is going to equal the delta H. Delta H is the heat of the reaction. So if it's endothermic, delta H is positive, and if it's exothermic, delta H is negative.